Thank you. Okay, so today I'm going to talk about approximation in the complex plane, polynomials, and then rationals. So let me begin. It'll be the same unusual mode as yesterday. So first, to say a general word about polynomials, it's remarkable how much of numerical analysis starts from polynomials, and that's been true since Newton, I suppose. And just to mention a few topics, interpolation, quadrature, approximation theory, root finding, optimization, ODE formulas, spectral methods for differential equations. Polynomials are absolutely the foundation of all of this stuff, not rational functions. Rational functions are more specialized but beautifully powerful, especially for people like us who love the complex plane. So regarding polynomials, if you want to work with higher order ones, you inevitably find yourself dealing with Chebyshev series if you're on an interval. So I'm sure you all know what Chebyshev series are. If you have a function on the interval that's Lipschitz continuous, that's more than enough to guarantee absolute convergence of the Chebyshev series. Chebfun is a software system built on this stuff, working with either smooth or piecewise smooth polynomials, the whole thing or the pieces represented by Chebyshev series. So we're very good at Chebyshev series. Here's just an illustration of a function in Chebfun, the good old Runge function. And there you see the Chebyshev coefficients of the Runge function down to machine precision. So Chebfun has computed coefficients using the FFT and decided that about here at 190 is the place to truncate. I forgot in the introduction to mention that Chebfun is available at this URL, and the text that I'm copying and pasting from is available here. So by all means, play along if you like. And for those of you who are interested in looking at it more carefully, please download that. I can't promise it will always be there. This is a draft version. I'm not publicizing it. So if you are interested, get that this week. I also, I'm just remembering, have 2 more hard copies. Is there anyone in the room who doesn't have a copy who wants to follow along? I see one there. Because the whole point is to go too quickly for you to understand in real time. So, was there anyone else? Right. So we deal with Chebyshev series. This is a very clean one, decreasing at a geometric rate because it's an analytic function in a neighborhood of the unit interval. Now, there are always 2 types of polynomials associated with a function. You can truncate a Chebyshev series, which is sort of the mathematically more obvious thing to do, or you can construct interpolants, which is the algorithmically more straightforward thing to do. So we call those Chebyshev projections or truncations and Chebyshev interpolants. If you represent them as a series of Chebyshev polynomials, you could say the coefficients are a sub k and c sub k. And the a sub k's, the Chebyshev coefficients, are related to the c sub k's, the interpolant coefficients, by aliasing formulas, which are well known. Here's an illustration in Chebfun of a particular function, which is the absolute value of x plus 0.1. And with just degree 3, we look at its Chebyshev projection and Chebyshev interpolant. So here I do that. You see the absolute value in black. The one that goes through the black dots is obviously the interpolant, and the red curve then is the Chebyshev projection. Notice there's not that much difference. There's no exciting difference between the accuracy of projections and the accuracy of interpolants. It's the same. The difference is in practical matters. Regarding how you might evaluate Chebyshev interpolants, I know 3 stable ways to do that. What makes the subject interesting is that the most obvious thing to do is catastrophically unstable. If you make a van der Waals matrix and then solve that problem, which is what everyone would think of doing, that's an exponentially unstable algorithm. However, there are various ways to do it stably. One is to use the barycentric interpolation formula. I learned about that from Jean-Paul Beroux. It's Herbert Salzer who published the relevant paper in '72. Another approach is just to compute the Chebyshev coefficients using the FFT, which is a perfectly good thing to do. A third approach is to use the Vandermonde idea, but with orthogonalization of the Arnoldi variety. I'll say slightly more about that in a moment, but mostly Yuji Nakatsukasa will be talking about that this afternoon. Chebfun used the barycentric formula for 10 years, and then it moved to the FFT approach, but that's not an important difference. It doesn't matter. You can do either one. So, for example, in the Chebfun gallery, we have an example called zigzag. So if you execute that command, you get this zigzag curve. The amusing thing is that's not what it looks like. That's a polynomial of degree 10,000. And we've just plotted before your eyes this polynomial interpolant in 10,001 Chebyshev points. It's perfectly stable. It's a terrible way to represent this function from an approximation point of view, but there are no issues of stability or robustness with polynomials of degree 10,000 or indeed 10 million. Now, as has been well known for 107 years, the convergence of Chebyshev series for analytic functions is determined by Bernstein ellipses, which are ellipses around the unit interval with foci at -1 and +1. The theory of that is completely analogous. It's a transplant of the theory of convergence of Taylor series on the unit disk. So you find that if you have an analytic function analytic in a Bernstein ellipse, bounded by m, then the Chebyshev coefficients decrease geometrically in that fashion. It follows readily that the Chebyshev truncations converge geometrically, and the Chebyshev interpolants converge geometrically at a rate maybe twice. There's a factor of 2, but no interesting difference between them. In Chebfun, you can look at an estimated Chebyshev Bernstein ellipse for a function with the command plot region. So suppose I say f is this Runge function, and then plot region of f. Of course, it doesn't know where the singularities are. All it knows is how long the Chebyshev series has to be to get down to machine precision. But that's enough to give an estimate, anyway, of the Bernstein ellipse of convergence. The actual pole is at plus or minus 0.2i, and you can see the estimate is quite close to that. Now, it's also been known from the days of Bernstein that if you have analyticity in a Bernstein ellipse, that implies a corresponding convergence rate on the interval, but it also implies convergence throughout the Bernstein ellipse. So as you go out to this boundary of your region of analyticity, you always get geometric convergence, but with coefficients that decay as you go towards the boundary. So let's illustrate that. I'm going to again take the Runge function, and I'm going to do a contour plot of how accurate the Chebyshev interpolant is through a region of the complex plane. So we'll see from the contour plot that it's super accurate on the interval and exponentially accurate within an ellipse and then useless outside the ellipse. So you see the contours I'm using are spaced by factors of 1,000, from 10 to the minus 15 to 0 in blue, and from 10 to the 3 up to 10 to the 15 in red. So this is accuracy of the Chebfun approximation, which is a Chebyshev interpolant, to the Runge function. So see, the blue is good. That's below 1. On the interval, the accuracy is about 10 to the minus 16th. And then the Bernstein ellipse, you can see the poles are the black circles. The Bernstein ellipse is the one that goes through those. You see within it, we have exponential convergence, and outside it, we have exponential divergence. So the accuracy here is 10 to the plus 15. That's not good accuracy. Whereas the accuracy there would be 10 to the minus 8th or something. Bernstein knew all this, but he didn't have MATLAB. Here, just to look at some numbers, I'm going to look at the error if I evaluate my polynomial interpolant at plus 0.1i, which is inside the Bernstein ellipse, or 0.3i, which is outside the Bernstein ellipse. And you see that half this 0.1i has an accuracy of 10 to the minus 9, 9 digits. But just 0.3i is 10 to the 8th, so it's complete crazy. Things grow exponentially outside your region of convergence. Now, is my plot still there? No, I have to get the plot back. Apologies. So I'll do it again. This is now that contour plot. And I want to now superimpose on the contour plot the roots of the Chebfun polynomial approximation. So this goes back to Jentsch's theorem, which for Taylor polynomials tells you that roots of Taylor polynomials converge on the circle of convergence. Well, of course, there's an analog for Chebyshev interpolants. Most of the roots converge to the Bernstein ellipse of convergence. So here, we take that contour plot and we superimpose on it the roots of the polynomial approximant. Isn't that beautiful? You see all these black dots are the roots. So that's Jentsch's theorem for Chebyshev interpolants. But now we can make it more beautiful. Everything is always very interesting and pretty when you do a phase portrait. So to remind you, a phase portrait is a portrait of a complex function colored by the phase, the argument. And Elias Vegert is the guy who's made these things famous. I'm sure you all know his calendars. The latest calendar just came out a week or two ago. So here we'll do a phase portrait of the polynomial approximant to the Runge function. So I really love that. So what you see is inside the Bernstein ellipse, we're approximating the Runge function, and the colors are essentially the colors of the phases of that function. But out you have then this collection of hundreds of zeros on the boundary, and then outside you have exponentially growing, beautiful, striped nonsense. All the zeros would be points where the colors come together on that boundary. Now, I mentioned a second ago the idea of Vandermonde with Arnoldi. This is the subject of Eugene Akatsukasa's talk this afternoon at 2:30, I think. This is something we've just been looking at in the last few weeks. Very exciting. I think people must have done this a bit over the years, but somehow it has failed to become a well-known technique. And the point is that the monomials z to the k are a beautiful basis on the unit circle, but on any other domain, they're an exponentially ill-conditioned basis. Now, if you're on the interval, you use Chebyshev polynomials, so that's fine. But if you're on other domains, not the circle or the interval, what do you do? There is, of course, a lot of theory about this, but it seems that in practice, it's surprisingly effective to just set up your Vandermonde problem, but instead of actually using that matrix, you reconstruct an equivalent matrix with the Arnoldi orthogonalization process. And that works really beautifully. And so please come to Eugene's talk. So this is something that is implicit in a lot of what I'm telling you for the rest of today, and especially tomorrow, in fact. We use this Vandermonde with Arnoldi now, even though we only became aware of it in the last few weeks. Okay, so now I want to move on to the rational part of the talk. Mostly I'm going to talk about AAA approximation and its relatives, and then at the end what we call AAA Lawson approximation. So, rational approximation. The famous type of rational approximation is pod A. In fact, I know people who say pod A and they mean rational. Pod A, properly speaking, refers to approximation at a point, maybe the origin, maybe infinity. You take a Taylor series, and rather than chop it to get polynomials, you approximate it by rational functions to a degree as high as possible. And you all know this. So, for example, if we take the function the square root of 1 plus z, That, of course, is analytic when z equals 0, but it has a branch point at -1, disk of analyticity of radius 1. Let's try to evaluate that function at 3 from its Taylor coefficients. The polynomials will do terribly, but rationals will do very well. So if I approximate square root of 1 plus z at 3, I'm taking 32 points, I guess, in the Taylor series. So you see the polynomial approximant is 10 to the 12th, which is not a good estimate to the correct value of 2. The Padé approximant gets it exactly. Very well-known effect. Very popular in physics. It became well-known in physics half a century ago. Mathematically, the business of extrapolation of series is more or less the same as this. So suppose you have a sequence or a series. In this way of writing it, I've made it a series. And it's slowly convergent. So you have a bunch of terms, and you're trying to add them up, but it's not converging very fast. Now, there's a huge literature on this subject, and one place to look is the recent book by Brzezinski. There are many ways to do this, but almost all of them boil down to some exploitation of Padé approximants. So one way to do, well, the idea is you take your function and you think of it as, you think of your coefficients as coefficients of a Taylor series. So you take your coefficients, imagine that they are coefficients of a generating function, and then our problem is to evaluate f at 1. So that's what extrapolation starts from, this idea of evaluating approximants based on their Taylor coefficients. So here's another example, which is mathematically just like the last one, but we think of it as a case of extrapolation. I have my function. I suppose I have the first 9 terms in the series. I want to add them up and find that would correspond to the value f of 1. So I'm going to print out the first 9 Taylor coefficients, and then I'm going to print the sum of them, which is the best you could do with a Taylor point of view, and then the Padé approximate of type 4 to them, which of course will do much better. So here you see I have Taylor coefficients that are converging very slowly, or these, I should stop calling them that. These are numbers whose sum is converging very slowly. You can see they're alternating and they're not decreasing very fast. So that's an annoying series to try to add up. If you view them as coefficients of a generating function and just add them up Taylor-wise, you don't get the square root of 2. But if you do it Padé-wise, you get 6 or 8 digits. So things like the eta and the epsilon algorithm and Wynn's algorithm are variations on this theme. Aitken extrapolation is the type N1 Padé approximant. Now, if you're on an interval, I'm not quite up to AAA yet, that's coming in a second. If you're on an interval as opposed to a point and you want to do rational approximation, of course, there are analogs with a Chebyshev flavor of Padé. And let me, in fact, mention 4 of them and plot 4 of them here. So I take a function, which is a hyperbolic tangent in this case, and I'm going to compare its minimax approximation, its Carateo-Dorothea approximation, its Chebyshev-Padé approximation, and linearized irrational interpolation, where we take, in fact, 100 roots of unity and find a least squares linearized rational approximation. These are all different analogs of Padé for an interval. And these are commands in Chebfun, so they're easy to play with. If I execute that, you find that minimax has equioscillation, which we all know about. CF looks essentially the same. For all practical purposes, it is the same for smooth functions. Chebyshev-Padé is not as good. Notice the error is about 10 times worse. And rat-interp also is not as good, but these are perfectly serviceable ways to approximate functions. Now suppose you have one of these approximations and you want to use it to extrapolate off the interval where you've approximated. of course, you can do that. You can evaluate the approximants elsewhere in the complex plane. And here we're doing that. You can see I'm going to take these 4 approximations and evaluate them at, I'm sorry, I've said that wrong. In this case, I'm trying to find poles of my function by finding poles of these approximants. So let's do that. And what you see here is that we have an error. What went wrong? What? I missed a bracket. Thank you. I've done more cutting and pasting in the last day than in the rest of my life, I think. So in this example, the exact pole would be there. You notice the minimax and CF approximants get it to about 3 digits. The reason it's 3 digits is that's how accurate the approximants are. The Chebfun and Ratenterp only get about 1 digit because they're only accurate to about 1 digit. And this is all floating point, yes, though I don't think that fact affects these numbers significantly. Everything in my talks, and this applies to my whole career, is floating point. So that's a general statement. Okay, let's move on to AAA. So AAA approximation is a very general way to do rational approximation, and it's happened at Oxford in 2016, and the 3 of us who did it are me and Yuji, and where's Olivier? Olivier Set. So we had this wonderful few months together exploring rational approximation, and we tried many different things, stimulated originally by Olivier's reading of this paper by Antulas and Anderson, and eventually came up with this thing which has proved to be more effective than we dreamed at the time. It really works beautifully. There are no theory about it. It's deeply nonlinear and greedy, but it really is amazingly fast and accurate in many cases. It's a general technique. It doesn't live on an interval. It lives on any set in the complex plane. And it exploits these barycentric representations of rational functions. So here's the barycentric formula. If you take just the right weights in that formula, you get a polynomial interpolant. But if you take other weights, you get a rational interpolant to some data. The idea of AAA is to pick those weights to get a good rational interpolant. So its accuracy, if you will, comes from choosing the weights. But the other half is to pick these so-called support points to get a stable representation, which P over Q will never work in rational approximation. And now floating point arithmetic is crucial. If you try to do anything with rational functions representing them by P over Q, it won't work. It's just unstable. Whereas barycentric representations can be outstandingly stable provided that the support points Z sub j behave well, and the AAA algorithm makes them behave well, it seems. It's quite extraordinary. So I'm, of course, not spelling it out in detail, but what I'm going to show you first is the convergence of the AAA algorithm when applied to this Runge function. So we take 500 Chebyshev points. We're now on just an interval. And we take the Runge function on the interval, and we apply AAA. So we're now getting a rational approximant, our 5th method, on the interval. So I don't know if you can see the dots, which are too small, but basically we start at degree 0, and as we get down to degree 6, we have this nice, clean geometric convergence to the Runge function. The algorithm's set up to stop automatically when it gets near machine precision. Now, this is not exciting on an interval. It's just a prototype of more general calculations. For example, if I looked at the poles of the approximation, I would find that there are 6 of them, and 2 of those are very close to plus or minus 0.2i. But now let's look on a complex set. So I'm going to plot for you here a set which consists of 1,000 or so random points. This is the set. It has 2 pieces. There's a bunch of points in a square and a bunch of points in a disk. we're now going to take a function on that set and approximate it with AAA rational approximants. The function we'll pick is the sine function, SIGN. So it'll be -1 on, that's, no, I think it's sine times z, if I remember right. -1 or two different components on the two sides. So let's do that approximation. So it very quickly finds some approximation whose length is 38. So that means it's a rational function of type 3737. And the error is 10 to the minus 12, so clearly it's doing pretty well. Let's look at a contour plot of the error. So this picture will compare the underlying function to its rational approximation in a neighborhood of these dots. And I think that's very pretty. Notice that we have the two sets here, and then the contours go basically from 10 to the minus 1 down to 10 to the minus 14. So you can see that it has somehow or other figured out where the data are. Of course, we haven't told it, you know, we haven't told it to work on a square or anything. It just knows that it has these points and data values at these points. And it's found an approximation that's essentially 14 digits of accuracy on those sets. Now, it's incredibly rare for a person like me to do a plot like that without including the poles of the rational function on the plot, because poles are so fascinating. So let's add them to the plot. So you can see that the poles line up in a beautiful fashion between the two sets. And you remember, this function is not globally analytic. It's analytic there and analytic there, but it's not a single representation. So you need some kind of branch cut separating the two. And AAA has put its poles here, so in some sense, that's the choice of branch cut it is making. So, as usual, the beautiful way to see such things is with a phase portrait. So let's look at that. So this is now the same example. You can see the dots where we've approximated, and you see the branch cut. So although the poles lie along there, somehow the deeper point is not the poles, but the fact that there's an approximation to a change of branch happening there. And we've seen this in some talks already, and I think there's some more coming. So the Nick Hale and Marco Fassandini and Andre Wedemann and others are doing remarkable things with these branch cuts right now. The AAA algorithm, like any rational approximation algorithm, you don't tell it where to put a branch cut. It figures that out. It's a corollary of its finding a good approximation on the black dots. It turns out that the strategy it has used to find that approximation has led to it putting some kind of approximation to a branch cut along this curve. So an analogy that I like to think of is that if you do a Lanczos iteration to compute eigenvalues, Lanczos's goal is not to compute eigenvalues. Lanczos is trying to minimize something. Why does it compute eigenvalues? Well, that's a side effect. It turns out isolating those eigenvalues is a good strategy for minimizing something. So that's analogous to the branch cut here being a side effect of an approximation. Here's another example. So let's stare at the equation here for just a second. I'm going to take the square root of 1 minus z squared. Now, it's going to be on a rectangle, and the two lower corners of the rectangle are -1 and +1, which are the branch points of that function. So we're approximating a function on a rectangle with, what is it? I guess I have a lot of points. I think I have 6,000 points delineating the rectangle. So we're approximating in those 6,000 points by a rational function, but they're the branch cuts at the corners. So let's see what that does to the poles of AAA. This will produce two plots. I think I saw an error there, did I? What was it? Oh, just a warning. We should kill that warning. It's annoying. So we have the 6,000 points delineating a rectangle. The function has branch points here and here. And AAA has computed an approximant whose poles lie on a curve connecting the branch points. And there's a lot of beautiful theory about the curves that rational approximants find delineating branch cuts. Herbert Stahl wrote a great paper on that for Pod A approximation, and then subsequent papers, they all seem to have a connection with Moscow, are by Aptyekarov and Swetine for more general types of approximation. Very beautiful phenomenon. So there you see it with the poles, and here you see it with the phase portrait. Within the rectangle, everything is analytic, but there are these branch points there and there with approximations to a branch cut in between. By the way, if you try to connect the dots with the phase portrait, you will be reminded that the dots are only the poles, not the zeros. So, for example, that dot is that pole, but this is a zero, and that's a pole, and this is a zero. So the poles and the zeros interlace along a curve. Now, tomorrow's talk has a lot to do with this. We're going to use ideas like this for solving PDEs and doing conformal mapping. And the key behavior is rational approximations near branch points. So we've seen the pretty curves, but from a numerical computation point of view, the real excitement is how those curves are accurately resolving something. And the magic thing is what we call root exponential convergence. Rational approximations can resolve a wide range of singularities, not with exponential convergence, but with root exponential convergence. O of constant to the minus square root of n for a positive constant. This was made famous by Donald Newman from Temple University in 1964, who wrote a very brief paper on the absolute value of x, proving that it could be approximated with root exponential convergence by rational functions. And the poles and zeros of his proof cluster exponentially near the singularity at 0. Well, this is a very general phenomenon. It applies to a very wide range of singularities on boundaries of approximation sets. And I want to show it to you with a plot of the convergence of the AAA algorithm for the example we just did. So the example was 6,000 points in a rectangle. We have the two branch points. According to the Newman principle, the convergence should be root exponential, and sure enough it is. So this next segment shows you that. I neglected to put a label on the axis, so let me emphasize. The x-axis is the square root of the degree. So when we see a straight line on this plot, that's root exponential convergence. So isn't that beautiful? It fools around for a bit. And then the straight line is showing Newman's effect applied now to a much more general problem on a rectangle computed by AAA approximation. But it's a very general effect. Rational approximants can do this root exponential thing near singularities. That's why they're important in numerical analysis, or one of the big reasons. As I mentioned, they achieve that root exponential convergence by having exponential clustering of the poles and the zeros near singularities. So let's look at that. The next little segment is going to plot the distances of the poles of my AAA approximant from the point 1. So we're looking at the bottom right corner of the rectangle. How close are the poles to that? So this is, of course, a log scale. What you're seeing is that the poles in our approximant have this beautiful straight line until the last few, which curves. And so the poles are exponentially clustered near the singularity. And notice they go down to very close. So the closest red dots on that picture were at a distance 10 to the minus fifth, 10 to the minus sixth. That's how rational approximations achieve their effect. It's a multi-scale sort of a thing. So the poles that are far away are handling data on a corresponding space scale. The ones that are very close are dealing with the very local behavior. So to an adaptive finite element person, this is obvious. If you do things on a multi-scale way, you can get fractional exponential convergence. And sure enough, you can. I want to talk for a few more minutes. So just to emphasize that point, I want to go back and plot again those two. Okay, so just to emphasize, the AAA algorithm has got 10 or 12 digits, I forget what. Oh, no, I think I specified tolerance of 8 digits. So it's got 8-digit approximation with a small number of poles. How does it do that? By exponentially clustering them. Let's zoom in so that we can see that. You can't tell from this picture how close the red dots are to the corner, but if we zoom in, you can start to see. So obviously there are red dots on a scale of 1, but zooming in, you can see on a scale of 0.1. Zooming in further, there we are on a scale of 0.01. Here we are on a scale of 0.001. See, the red dots are really clustered. And this behavior, which you might think of as kind of just a matter of approximation theory, is crucial for numerical algorithms of the kind I'm going to be showing you tomorrow. Okay, the final bit of today's masterclass is about what we call AAA Lawson minimax approximation. So, to remind you, the AAA idea starts from a barycentric representation. And I didn't say what AAA stands for. It stands for Adaptive Antulas-Anderson. And the Antulas-Anderson idea was to use a barycentric representation to interpolate a function in a bunch of points, but also have good coefficients so that it would be a good interpolant. Now, if you want to get a minimax approximation, you can't interpolate because you want to equioscillate or whatever to get the true minimax. So an interpolant is too constrained to do a minimax approximation. So there's this notion of using barycentric representations in a non-interpolatory fashion. We call it alpha-beta mode. The idea is you have the same kind of ratio of partial fractions as usual, but the data f sub j is no longer in this picture. You now have coefficients alpha sub j for the numerator, partial fraction, and beta sub j for the denominator, partial fraction. And you're going to pick those by some kind of linearized least squares process in order to minimize a L2 norm on a discrete set. So you could do that, and you'd get some kind of approximation. But now the Lawson idea is you start by minimizing an L2 norm, but then you make it a weighted L2 norm, and you iteratively adjust the weights until you get a L infinity best approximation. So that idea goes back to Chuck Lawson in 1961, wrote a thesis about this at UCLA. The phrase is iteratively reweighted least squares. That also appears in compressed sensing a bit. I'm surprised actually it isn't a more famous idea. It's such a simple thing and it really works. For linear approximation, you can prove it works in various contexts. That goes back to the 60s. For our nonlinear barycentric context, we can't prove that it works, and indeed it doesn't always work, but it surprisingly often does. So our AAA Lawson algorithm has this alpha-beta mode. First we run ordinary AAA to get a good set of support points, which then never change. So we run ordinary AAA to find these ZJs. Then we go into a phase of Lawson iteration, iteratively reweighted least squares, to hopefully converge towards the L infinity approximation. So you end up with an algorithm for minimax approximation on general complex sets. That turns out to be an area where there's hardly anything out there. The best known paper is by Ellicott and Williams in 1976, but there's really not much rational minimax approximation on general complex sets. And this seems to work pretty reliably, not always, but often. So I'm going to finish with two examples of AAA Lawson, first on a real interval and then on a circle. The way it works in Chebfun is it's all part of the Chebfun AAA command. So most of today's lecture is in Chebfun under AAA. If you just call AAA, you don't go into this Lawson mode. It just finds a good approximation, hopefully to 14 digits. But if you specify a degree, it goes into AAA mode and tries to give you minimax, unless you tell it not to, unless you say, no Lawson steps, please. So this command will do plain old AAA for 15 steps. This command will do AAA for 15 steps, followed by the iteratively reweighted least squares for, I think, 20 steps is the default. And it'll plot the error curves so we can compare straight AAA with AAA Lawson. So the blue one is the type 15 approximant that AAA gives you. Notice it oscillates a reasonable number of times, but it doesn't equioscillate. It's obviously not optimal. But then after 20 steps of Lawson iteration, we have the red curve, which does equioscillate, so obviously is optimal. This is not the best way to compute on an interval. You can use the Remez algorithm and the Chebfun minimax command, but I'm just illustrating how AAA Lawson can also do the job. But much more exciting is complex approximation. So the final example is on the unit circle. So here I now take my set to be 1,000 roots of unity on the unit circle, and I'm going to approximate e to the z by degree 3. First of all, I'll do it just with straight AAA without Lawson, and then I do it by AAA with Lawson to get a minimax approximation. So the blue curve, this is now an error curve in the complex plane. It's the image of the unit circle under the error, the difference between f and my rational approximant. AAA gets in the ballpark. It's got the right order of magnitude of the error, and you can see it's a blue curve that winds around a bunch of times. But AAA Lawson really gives you the minimax, which is it's not exactly a circle, but it's incredibly close to a circle with a winding number of 7, that being the right thing for type 3-3 approximation. So we know other ways to compute best approximations on the disk, CF approximation in particular, but this same method works on much more general sets, and in practice, I think this is the first practical method for computing rational approximants on general sets in the complex plane. Okay, so once again, I finished a little early, so I'm happy for questions if that's okay. Somebody was asking me about that at coffee. I don't know how to do it. That's a very interesting question. You mean, for example, is it a square root or a cube root or something? I don't know how. Does anyone know how? A lot of us are interested in that. Yeah, I can do it. You can do it. So please tell us over coffee how to, or unless it's very quick. Yes, yeah. Good. Is that in your talk?
No, I don't think it's. Basically, you look for distribution of points in singularities by which law they approach.
Yes.
Accumulate, and then from this you can extract this power law.
Really? So you can distinguish a square root from a cube root?
Yeah.
Beautiful.
So okay. A precision, some maybe the double precision might be not sufficient in some cases.
Ah, okay. I see. Okay.
Yeah, it is robust.
Okay.
If you have a general complex set,
Yes.
and you're trying to keep the set of discrete points, would that be necessarily the, like you take think of a conformal map that sends you a circle, and then the points that correspond to uniformly spaced out points in the circle, the images.
Right. So the question is how to pick sample points.
Would that be the optimal?
So I think what you're describing is called Fekete points. I don't use that at all because in order to do approximation, I want to do something easy. We throw down many more points than that. The whole point is not to try to find the optimal because that's nearly as hard as the problem you're trying to solve. But yes, of course, there is a whole theory of uniformly distributed points which are related to conformal maps. Related to the choice of points on the boundary, a crucial thing, if you're really doing this stuff with root exponential convergence, because it's operating on these different scales, you need to sample on those scales too. So if you look at the code there, you'll find the hyperbolic tangent of Lin space from -12 to 12, which is an incredibly clustered grid. It's crucial to sample in a very clustered way near the points. And which, by the way, highlights that rational approximation demands somewhat different things than polynomial approximation, because what you were describing would be relevant to polynomial approximation.
In your class on 3.1 theorem about rational approximation, you have integral -1, 1. Right? But for instance, factorization problems, very often we need approximation of the whole real axis. Is there any progress on that?
Well, I don't know what you mean by progress, but AAA does work on the whole. Yes, oh yes, we have a...
Then you probably need, since the degree m could be very high, you also need, I mean, not you, it's very useful to have information about the zeros of functions.
Well, there's a lot going on here. Mathematically, there's no difference between the whole real line and the circle when you're in the rational context. So it's not obvious that you need more information. It all depends on what you're approximating. I agree there are complicated functions that are hard to approximate, but whether it lives on the whole axis or a bounded domain, I think is not the essence of the matter for rational approximation. So Manfred's asking, can we predict when it fails? This is very interesting because it doesn't just fail because of rounding errors or something. It's deeper than that. There's a fundamental problem. And weirdly, it shows up 10% of the time rather than 99. We don't know why. So that's an important thing we're trying to figure out, and we don't know. Very crudely, if you don't have enough, it depends on where the points are clustered. If you don't have enough points where the action is, the algorithm often fails in a fundamental way and truly diverges. But we don't really know why yet.
More questions or comments?
Can I make one more comment? So I mentioned that Yuji is speaking this afternoon on Vandermonde with Arnoldi. But the other related talk this afternoon is Abhi Gopal here. Are you at 3:30? Oh, so Yuji, you're at 1:30 and 2:30. So these are very different talks, but both related to this. So Yuji's talk is about polynomials and how you can stably approximate with polynomials by orthogonalization, Arnoldi style. Abhi's talk is about this root exponential effect. I'm just talking about analytic harmonic functions and Laplace's equation, and tomorrow I'll be doing that. But Abhi is actually doing the harder problem of the analog for the Helmholtz equation. So anyone who's interested in Helmholtz definitely needs to come to Abhi's talk at 2:30.
Thanks.